Okay, guys, welcome. In this video, we're going to talk about primes and their history. Now, we say that an integer that's greater than 1 is called prime if it's not divisible by any integer other than 1, -1, p, and -p, right? So we say that an integer is prime if it cannot be written as the product of two smaller positive integers, right? So the only way to write it is a product of 1 and itself, or -1 and negative itself. Okay. Now, an integer that is not prime, we say is composite. Now, one thing to keep in mind here is that 1 is technically not prime nor composite, right? Because its definition is kind of circular, right? If you go to prime, right? So we consider 1 to be neither prime nor composite. Now, one thing that we did previously is that we proved that there are infinitely many prime numbers. Now, unfortunately, other facts about the occurrence of primes are a little bit harder to come by, right? So their sequence is somewhat smooth, but there are holes and dense spots, right? So for example, like if you look at the first couple numbers, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, we'll just say. We know that the prime numbers are 2, 3, 5, and 7, right? So out of those first 9, you have 4 of those are prime. Then in the next set, you have 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. And then in this next set, you have that 11, 13, 17, and 19 are prime, right? So then you have 4 more again. But this pattern, of course, won't continue forever, and you do get some spots where you have consecutive odd numbers are prime, but then some where consecutive odd are not necessarily both prime, with 15 and 17, and so on and so forth. Now, of course, one example question that you might ask is, are we certain that there is a prime number with any given number of digits, right? So if you have, say, a 10-digit number, is it guaranteed that there's a prime number with 10 digits? Now, the answer, of course, is yes, but this was not proved until the mid-19th century, which is new among mathematical results for number theory anyway. And there's a lot of similar questions that are currently unanswered. Now, with the use of computers, we have more power to investigate primes, right? Now, one thing that you could do is you could test all smaller positive numbers to see if they are a proper divisor, but for large numbers, of course, this becomes impractical. Now, we have much more efficient algorithms, and we can now fairly easily determine if a number with 1,000 digits is prime or not. Okay. Now, a fact about composite numbers is that any composite number can be written as a product of only prime numbers, right? So for example, if you take the number 25, for example, you can write that as a product of 5 times 5, right? And both of those are prime numbers. Now, of course, you could also do something like 30, right? You could break into 6 and 5, but 6 can be broken into 3 and 2. So you can multiply it by 3, 2, and 5, right? Now, as a matter of fact, you can always do this uniquely, which means that for any number that you pick n, there's only one way to use the primes to write that number as a product. And of course, this is known as the fundamental theorem of arithmetic. This says that every positive integer can be written as the product of primes, and the factorization is unique up to the order of the prime factors, right? So which just means that we say that 2, 3, and 5 is the same as 5 times 3 times 2. Okay, now what we're going to do is we're going to use a version of induction, which is sometimes called the minimal criminal argument. And we'll also use contradiction along the way as well. So we're going to assume that there does exist an integer n with 2 different factorizations, right? And that this is the smallest such integer that this happens for, right? So we'll say that n can be written as p1 as a product from p1 to pm, and also from q1 to qk, right? And of course, it's possible that we do have that sets of primes are the same, right? So instead of using powers here, we're just using that we have this list of primes that may or may not be the same. But whatever this product is the same as this product is the key idea of this proof. Now we'll assume that without loss of generality, that P1 is the smallest prime here. And by without loss of generality, I mean that we could have just as easily chosen Q1, right? And the argument would sort of work in a symmetric fashion. Now, we claim that we can produce a smaller n star that also has more than one factorization, which will give us the contradiction that we want. Now, if P1 is not one of the QI, no, that it's not one of the QI, right? P1 is not one of the QI, or else we could divide both sides by P1 and we could get a smaller number, right? So we could divide both sides by P1 and we would still have a list of primes left, and that would be a smaller number n, which would be a contradiction. Okay, so P1 is not one of the QIs, all right? So what we're going to do is we're going to divide each QI by P1, and they each get their own remainder, which we'll refer to as Ri, right? Now we're dividing a prime by another prime, so we know that each of these remainders is non-zero, right? So now we claim that if we take the product of these remainders, we'll get 2 factorization and n star is less than n, right? Now, note that your remainder in each case is less than P1, right? Because we're dividing by P1, so it can't be any bigger than, it can't even be as big as P1. And each of the P1s are less than QI, right? So what we could do is we could say that n star, which is the product of the Ri's, is strictly less than the product of the QI's, which is our just regular n. Now P1 divides n star, right? This product of these remainders here. Since we can write each of these Ri, right? If we go back and we solve this equation here where we had, what was it? It was QI equals, let me see what it was, P1 times AI plus Ri. We could solve this for Ri, and we would get QI minus P1A1, right? So all I'm doing from this step to the next step is that each of these are my R's, but we've just reordered this equation to write them in this way, right? Now, if we expand this, every term is going to have a P1 in it, except for the first term, but the first one is Q1, Q2, all the way through QK, which is our n, which we know is divisible by P1. Right? So we know that we have every term is divisible by P1. And now basically we have it, because if you divide n star by P1 and then factor n star over P1, right, what we just did, you get a factorization of n star. Now P1 occurs in this factorization of n star, but not in the original definition, which was the product of the remainders, right? And there's our contradiction, right? So that goes to show that any positive integer can be written as the unique product of prime numbers. Okay, so let's do some more proofs involving some primes. So I'm going to prove that if P is prime and A and B are integers, and we know that P divides A times B, then either P divides A or P divides B or both. Okay, so let's go ahead and we'll say that if P is prime and we know that P divides A times B, well, then that means that P times some K is equal to A times B for some integer K. Okay, now we want to show that either P divides A, which means that P times L is equal to A for some integer L, or P divides B, which would mean that PM is equal to B for some integer M. Okay, so that's what we want to show. So now, one way we can do this is, let's assume that P doesn't divide A, and then we'll show that P has to divide B. Okay, so if P doesn't divide A, then we're going to have some kind of remainder, right? If this happens, we know that we're going to get A is equal to P times Q plus R for some Q. Okay, now going back to P dividing A times B, that would mean that we get PK is equal to A, which is PQ plus R times B, right? Now, if we divide, let's see here, actually, here's what I want to do. Because we want to be able to write this as P times some integer M, right? So let's distribute this right side out, and we'll get a PQ times B plus B times R, right? Well, now I can factor, wait a minute, let's see. Do I have it? All I want to do is I want to show that P times M is equal, oh no, I need to move this over. Okay, so let's go ahead and let's see. So let's go ahead and move our P term over. So PQB, we're going to move over. And now we have that P times K minus QB is equal to B times R. Now, you know what? Am I complicating this? Let's see. Let's come back here for a second. Okay, so what we want to show is that P times some integer is equal to B. All right, so if I substitute this in here, I know that my A is PQ plus R, and that times B is equal to P times K. Okay, so now what I want to do is, let's go ahead and divide both sides by PQ plus R. And we'll get that B is equal to PK over PQ plus R. Right? Now we want to be able to write this PK over PQ plus R as P times something. Right? So how can we do that? Now, it doesn't seem like that's entirely obvious, so let's try a different approach. So we're going to try another approach. Now, one way we could do this is we can consider the prime factorization of AB. Right? Now, since P divides AB, we know that P is somewhere in here, right? So we have P and then times, let's say, J1, J2 through JM or something like that. Now, since this is made up of A and B, that means that regardless of how we choose this, these are partitioned into two products, right? One is A and the other one is B, right? So this sort of completes the argument that P either divides A or P divides B, or it could be both if P occurs more than once. All right, so it actually turns out that there's a much simpler argument to prove this, right? And that's sort of the idea. Okay, now let's suppose that A and B are integers and A divides B. We'll suppose that P is prime and that P divides B, but P does not divide A. And then we want to show that P is a divisor of B over A. All right, so first let's say A divides B. So if A divides B, A times M is equal to B. Now if P is a prime, and also P divides B, we know that P times K is equal to B. And I should be saying that M is an integer and that K is an integer. Okay. Now we also know that P does not divide A. P does not divide A. So if we wanted to, we could say that A is equal to QP plus R. And now we want to show that P is a divisor of B over A. So we want to show that P divides B over A, which means we want to show that P times, let's see, P times L is equal to B over A. Well, first of all, how can we write B over A? B over A is equal to, one way we could say this is AM over A, which is M. All right. Now, is that helpful? Maybe, maybe not. Okay. Another way that we could say this that might be more helpful is that B over A, now let's leave B as P times K, and then A we'll say is QP plus R. And we want to be able to write P times something to give this. Okay, so now let's see how we could maybe do this. Now, one way we could do this let's see. So what we could do, so again, we're kind of in the same situation as we were last time where it's maybe not clear what to do. So now the trick here is to think of, we know that P divides B, and another way to think of this is that P divides A times B over A, right? Because that's the same thing. Now we know that P does not divide A. So by the problem that we just did, P has to divide B over A. Right? So that's, again, using the fact that if P is prime and A and B are integers, P divides A times B, then it divides one of them. In this problem, we knew that P did not divide A, so it has to divide B over A. Okay. Now, this next theorem is on composite numbers, and this suggests that for every positive integer k, there exists k consecutive integers that are all composite. And of course, the way to do this is to let n be equal to k plus 1 and consider n factorial plus 2, n factorial plus 3, all the way to n factorial plus n. Now, the claim is that all of these numbers are composite. Now, of course, n factorial plus 2 is even, since n factorial and 2 are both even. N factorial plus 3 is divisible by 3, since n factorial and 3 are both divisible by 3. And in general, n factorial plus I is divisible by I. And of course, this works all the way up to n. So we have found n minus 1, which is k consecutive composite numbers. Now, the opposite question is to find primes that are very close to each other, right? Can we do that? Well, the difference between two primes must be 2, except for the two numbers 2 and 3. Now, primes when the difference is 2 are called twin primes, right? So 3 and 5, 5 and 7, 11, 13, 17, 19, some examples we looked at earlier, are all examples of twin primes. Now, it's still not known if there are infinitely many twin primes. Surely there are, of course, but there's no proof that exists currently. Now, one important question about primes is how many primes are there up to a given number n? We denote this by pi of n. Now, if we look at pi of n from 1 to 100, we see that it's sort of increasing here. And it looks like we're at about 25 primes between 1 and 100. Right, and if we look at this up to 2000, it looks like we're going past 300 at around 2000. Right, now there's no exact formula for pi of n known, and it's probably basically impossible to obtain. We do have a powerful result that's almost as good. Right, and this is known as the prime number theorem, and this lets, if we let pi of n denote the number of primes from 1 to n, then pi of n is asymptotic to, and we'll talk about what this means again in a second, asymptotic to n over natural log of n, right? And this essentially means that if you look at the ratio of pi over n, the true number of primes among 1, 2 through n, and you divide that by what we're saying that it's equal to n over what it's asymptotic to, n over ln of n, that means that this ratio approaches 1 as you make n approach infinity. Now, the proof is fairly difficult, so we're not going to cover it. But that is the conclusion of this video on primes. I hope you enjoyed, and I will see you next time.